Andrew Wood, and this is the Physics 2212, Lab 5, Magnetic Braking, Faraday's Law. For the introduction, the purpose of this lab is to observe how a magnet falling through a conductor reacts and to determine what forces are causing this interaction. We will also build a computer simulation to determine the effects mathematically along with experimentally. For my results, my experimental time was 2.008 seconds on average. My computational time was 1.99 seconds. Physics principles. The properties we are using in this lab are Lenz's law, Faraday's law, the Biot-Savart law, magnetic flux, and Newton's second and third laws. We'll also be using the equations on the right. Procedure and experimentation. First, for the experiment, we define the north pole of the magnet and orientate the roll of foil that we are using vertically. Second, we had to record dropping the magnet through the tube of foil. And third, we had to use the video to calculate the time it took for the magnet to fall through the conductive tube of foil. For my experiment, my length of foil was 0.3 meters, the width was 0.02 meters, the inner radius was 0.018 meters, and the outer radius was 0.020 meters. The mass of the magnet was 0.0225 kilograms. The magnetic dipole moment was 1.853 meters squared. Experimental results. For trial 1, I got 2.1 seconds, trial 2, 2.01 seconds, for trial 3 and 4, 1.99 seconds, and for trial 5, 1.95 seconds. The average trial time for the magnet to fall through the tube is 2.008 seconds. This experiment was repeated 5 times to ensure accuracy of the test. For my GlowScript encoding, I first changed the length, width, and inner radius to fit my experiment. I then changed the mass of the magnet and the magnet's magnetic dipole moment to also fit my experiment. I then used my coding from Lab 3 and input it into the dipole moment formula, or B field magnet. For continuing my coding, I then changed the force of gravity to be a vector in the negative y direction of mass times gravity. The next thing I changed is the B at ring to equal to the dipole of the bar magnet and the r radius of the ring. I then took the normal of that and for sine theta, I then took the magnitude of the cross product of mu hat and b hat. Then for the magnetic force on the ring, it was the absolute value of the ring current times 2 times pi times the ring radius times the magnitude of the B field at the ring times sine theta. Then on the right, I made it so that the bar velocity equals to the force over mass times delta t plus that bar velocity at that time, and the bar position at time equals to the bar position previously plus bar velocity times delta t. Then a preview of the graph. Results. We know by Lenz's law that the blue coloration in the tube is the clockwise rotation of the current. The red coloration is the counterclockwise rotation. If the magnet was flipped, the same result would occur because the current is not correlated to the direction of the magnetic field, but the direction of the flux on the magnet. We also have the graph on the left. Errors in analysis. Experimental time was 2.008 seconds, and the computational time was 1.99 seconds. Errors might have been introduced because the magnet or the tube is not consistent throughout and has variations in diameter or thickness. There could also be errors introduced in the video analysis and the timing of the drop. The shape of the curve tells me that the magnet enters through the tube over the velocity it can sustain and then rebounds with more forces acting to slow it down. It then drops again to the equilibrium velocity of it falling inside the tube, and as it reaches the end, less forces are acting on the magnet and slowing it, so it begins to accelerate down again. What if, because current and resistivity are inversely proportional, if the resistivity of the tube were to reach near zero level, then the current generated inside the tube would be great and slow the fall of the magnet even more? For the second what if there were lots of holes or slots cut into the tube, the magnet would fall faster. This is because the holes in the tube would interrupt the current flowing and overall make the tube generate less current and making the forces acting on the magnet less. I'm Andrew Wood, and this is a Physics 2212 Lab 5.